The following content has been provided by the University of Erlangen-Nuremberg.
So good morning, welcome to the second lecture of the quantum theory course. As we said last time, a Hilbert space underlies quantum mechanics, and the Banach space is a generalization of a Hilbert space. And it's a slight generalization. And the reason why we're looking at it is not because we want to be general for generality's sake. It is rather that if we look at Hilbert spaces, very quickly we will look at operators, linear maps on Hilbert spaces, and such spaces like, for instance, the bounded linear maps, which I will define today, they constitute a vector space again. It will be a normed vector space. It will be a complete normed vector space, but it will not be a Hilbert space. It will be a Banach space. So even if we start with Hilbert spaces, as we would like to focus on in quantum mechanics, in line 2, we need Banach spaces anyway. So we start with them. And obviously everything that's true for Hilbert spaces is true for, what's true for Banach spaces is true for Hilbert spaces too. There's generalization of a Hilbert space, but also appears from constructions that start with a Hilbert space. So what is a Banach space? Definition. If you have a Banach space is a vector space, so it's a vector space V with a vector space addition and S multiplication, and it's additionally equipped with a norm. So it's a vector space with a norm. Now, what is a norm? A norm is a map that takes an element of the vector space into the real numbers. So even if we're looking at this complex vector space, nevertheless, a norm takes you into the real numbers, and it satisfies the following properties. If you look at an element V, small v in capital V, let me call it F, let me call the elements of a Banach space F, and you multiply with a number from the field over which the vector space is taken, let's, in our case, always take the complex numbers, then this is the absolute value of the complex number times the norm of this vector. The second condition is that it satisfies the triangle inequality, so F plus G norm will always be less or equal to F norm plus G norm. And the third property is that the norm is always non-negative for all F in V, and equality is assumed if and only if the F itself is the zero vector in this vector space. So Banach space is a vector space with a norm which is complete. So there is it again, this completeness property we already had for Hilbert spaces, which is complete with respect to this norm. And I remind you, to be complete means that if you look at any Cauchy sequence in the space, you may already conclude that the sequence converges. Every convergent sequence is a Cauchy sequence, but the converse does not hold. Okay, now a standard topic in mathematics is you study a structure by studying maps between different instances of that structure. And that's not different here. So study maps of the following type, A, that start in a vector space V. Well, actually, a map starts in a set, and it goes to a set, and the set may have further structure. And we go as far as saying the set that is the target set here, this should be a Banach space. So it comes with an addition, an S multiplication, and a norm which in order to distinguish it from other norms is called the norm down W. Now, well, in the future, I will increasingly not write down the plus and the S multiplication and so on. And we would like to be as general as admitting that the domain of the maps we're looking at are only normed spaces. So this is only supposed to be a normed space, which means it also has an addition, an S multiplication, and the norm, but we do not require completeness. For the target, we require completeness. For the domain, we don't. So this is a slightly weaker assumption than if I assume this also needs to be a Banach space, and that will serve us very well that we do it in this generality. Okay, so we we study such maps, and and so we have the definition, a map A. I think I should, a map A is bounded. A is said to be bounded if the following is true. If you take the A and you apply it to any F from the domain, then you take the norm and you normalize this by the F up here. And now you look at all the F's from the domain and you take the supremum of these numbers here. So this is the smallest upper bound. And if this is finite, so that's the condition, if this is finite, then the A is said to be bounded. Now it's often useful to rewrite this, you see, because of the, well, it's not the linearity of the norm, but the linearity up to then taking an absolute value of the norm. If you scale the F down to a unit vector, meaning that the F has norm 1, then we have a 1 down here, and the scaling factors cancel. So we often look at only all the F's that are unit vectors with respect to the norm, and we only need to look at the AF. Now, obviously, here you need to take the norm on the target, and here you take the norm on the domain. So this is also the norm on the target, and this here is the norm on the domain. A is said to be bounded if that is the case. Now, if we have such a bounded operator, we have the definition. The operator norm, and that it's a norm in principle needs to be shown, but it's straightforward. The operator norm of a bounded operator. Of a bounded operator is the norm like so, and I do not write anything here. So if it doesn't have an index, it's the operator norm. And increasingly, I will not write indices anywhere on norms because it's clear from context. This can only be the norm on the domain, this can only be the norm on the target, and this can only be the operator norm, right? But maybe for a while it's good to focus on that. So this is then the supremum of all unit F on here of the AF here. So if this number here is finite, then we call it the norm of the bounded operator. Now, why do we look at bounded operators? And the answer is they are very important technically, but in fact in quantum mechanics we will need, and actually all the requirement to do these deep mathematics in functional analysis is that we need to deal also with unbounded operators. But the bounded operators are an important step to there, because many of the proofs for unbounded operators you always try to reduce to a sequence or something of bounded operators, and then you deal with that. Okay? And for unbounded operators there is no such norm. So we start with this as a subclass of important operators, and we will generalize later. Any questions so far? I do have one. Where's the... Oh. So I'll instantly present two examples for a bounded operator and for a not bounded operator. And the example for the not bounded operator is technically still different from the so-called momentum operator in quantum mechanics, but it's very similar to it, and we'll come to the proper momentum operator. But already here we get a taste for it, that the momentum operator in quantum mechanics will not be a bounded operator. And neither will the position operator of quantum mechanics be a bounded operator. So actually everything that's true for bounded operators, for instance, that you can write down commutation relations between them, you cannot do for unbounded operators. So if you maybe saw before the commutation relation Q with P equals IH bar delta, you cannot even write that down. Anyway, so we'll come to that. So example. You can write down something different, but that itself you can't write down. So let's do an example for a bounded operator. Well, let's take V to be the same as the W, so they both must be Banach spaces. And consider the identity map on W. So the map that takes W to W linearly, from a Banach space to the Banach space. What map is that? Well, it takes an F to an F. And so what is its norm, if it exists at all? What's the norm of the identity operator? Well, you look at all the normed Fs, and you look at the norm of the identity W on F here, but that's obviously sub norm of F equals 1 of the norm of F. Well, that is clearly 1. So the identity map is bounded, and hence we can write down the norm. So in principle, I can't write this until I found it's finite, and then the norm is 1. That's the operator norm of the identity map. It's, of course, a particularly simple example. Let's do not such a simple, but very instructive, as I indicated, counterexample. Let's construct a not bounded operator. So we again need to get ourselves a Banach space, and this time we look at the space C0 over an interval 0, 1. What is this beast? This is the space of all real functions, or let's take complex real. Oh, let's let them be complex. It's more quantum mechanically. All functions that are defined on the closed interval, and the closed is important here because it needs to be compact, into the complex numbers such that f is continuous. And you know how that works. You have a topology here, you have a topology there, maybe the induced topology from the real numbers or something like this, and a map is continuous if the pre-image of any open set here is open in here. Okay? So let's take the set of all continuous functions. Now, in order to make it a normed space, we need to invent a norm on it. And the norm we invent for this particular purpose is called the supremum norm or the maximum norm or the infinity norm, whatever. It's very easily defined. It's simply the you take the supremum over all the x in the domain. That means from any x in this interval, and you look at the supremum of the absolute values of the function. Okay. Sorry, it's not a set, of course. That's the supremum norm. And now one can show, and maybe I put this on a problem sheet, but now for the purpose of this example, you believe me, one can show that W together with the supremum norm is complete. Well, we also had to check why is this a vector space in the first place? Well, because you can add functions. Why can you add functions? Well, you can inherit the addition here from the addition on the target pointwise defined addition and S multiplication. Is that clear, or shall I make a comment? Comment? No. Yes? Okay. Yeah, please very quickly say it and I do it. So in order to see that this is a vector space, this W is a vector space, what do you need? You need, first and foremost, two maps plus W to W, and you need an S multiplication from the number field, it's a complex vector space, into itself. Now, how can we afford such a map? Such two maps, an addition and an S multiplication? Well, we define the sum of these two, so it's the sum on W. We define it, because these are functions, because W is this thing, we define it as the function which at each point x takes the value f of x plus g of x. Now this plus is the plus in the complex numbers. Hence I can say I inherit a plus on this space from the plus on here. This is the addition on the vector space, this is the addition on the complex numbers. And similarly, I have a S multiplication here, multiplication by an element in the field that's defined pointwise by the multiplication, the complex numbers pointwise here. Okay, now you have to check, once you did that, you have to check that Kani and Adu, these 8 axioms are satisfied. And once you've done that, you have a vector space. Once you have that, you have a norm. Well, you need to show that you have a norm. So you show the 3 properties, 1, 2, 3 of a norm. Then you have a norm, and then you show it's complete, and then it's complete. And then in total, you conclude that the whole thing is indeed a Banach space. Okay, I mean, I provide this as an example. This is for you to fill in the individual steps. And you do this once or twice or 3 times, or later on, anytime you're in doubt whether it's really a Banach space or not, you check, okay? Sometimes you believe, because otherwise we do nothing else anymore than proving these things, okay? But this is what you need to check. So now we have this. Now, however, I do not want to have a map from W to W. I want to define a map P from the following space into this W, into this space of continuous functions on a compact interval, which dressed with this structure is a Banach space. And we know for the linear maps we look at, we do not need a Banach space here. We only need a normed space, right? And what I do here for this example, I take C1, not C0, but C1. That's not the functions that are continuous, that's more special. Those are the once continuously differentiable functions. Once continuously differentiable functions on 0, 1. So now listen carefully. To be continuously differentiable means you can differentiate and the result is continuous. That is what continuously differentiable means. Now, if you can differentiate, that means it's at least continuous. So what we see here is, of course, it's clear that C1 is a subset of C0. Is that clear? But it's more than a subset, it's even a subvector space. What you need to show beyond subset. So because every differentiable function is continuous. It's a subvector space because the sum of any 2 differentiable functions is differentiable, and a constant multiple of any differentiable function is a differentiable function. Hence, it's even a subvector space. Aha! But if it's a subvector space and we had a norm up here, then it inherits a norm from the norm on this space, because I simply take the norm on this space, which I constructed, this maximum norm, and I only apply it to the fewer elements. So it trivially inherits a norm. Okay? What is not guaranteed, so if you have this, and then with the maximum norm from over here, also with the maximum norm equipped, this is Banach, but this may only be normed space. Why? Because I took elements out. It's a subset. If I take elements out, it could be that you have a Cauchy sequence in here, which you know converges, but imagine just the point it converges to, you had to take out to get here. Then it's no longer complete, because the Cauchy sequence no longer converges in that set, because the limit has been taken out. So if you start here, you go here, this may only be a normed space. But we don't care, because all we did is already doable if this is only a normed space. Okay? So we look at this, and now I need to tell you, so I say I want to construct a map from here to here. It's a concrete example, so that's why it's so specific. And I take an f, I take a once continuously differentiable function, and I map it, high school mathematics, to its derivative function. Okay? Well, that is a simple enough map. So it's the differential operator. I could have called it capital D or so. It's the operator that makes out of a function its derivative function. Very simple thing. Is this a linear operator? Clearly linear. Why? Well, you know why. P of f plus g is f plus g prime is f prime plus g prime is p of f plus p of g, and similarly for the rule, if you multiply by a complex number, ta-da-da, it's lambda times the derivative of this thing. So it's clearly a linear map. It goes from the right space into the right space, but the point is, I claim it's unbounded. P is not bounded. I should call it not bounded. In the literature, people say, let this and that be an unbounded operator. And what they mean, we don't say whether it's bounded or unbounded. We don't know. Let's assume both. So unbounded means we're not making assumptions on it. Not bounded would say it's definitely not bounded. But very often one says out of language habit, unbounded, and one wants to emphasize it's not bounded. Okay, so you need to be careful with the literature, and even more so with what I say here in the heat of the moment. So, but why is it not bounded? Well, it's useful to look at that in detail. You got this, right? Let me. So let me give you the argument why it's not bounded. And as often with such arguments, at first sight you say, oh, I would have never gotten the idea to look at it like that. But then you look at it again and you say, oh, that's a good way to look at it, right? And then in future examples, you already gained one tool in your toolbox of how to look at things. That's the reason why I present all the proofs here. I mean, virtually all the proofs. Because the proofs are as important as the results, because they really tell you how to deal with things, and you learn very useful tricks. If you don't learn them, you can cite all the theorems and you can do nothing with it. That's not particularly useful. So the claim is it's unbounded, and well, the proof for that is as follows. Sorry? Also true. It's also true. It's not bounded. So the proof is the following. Consider the sequence, a very specific sequence, in the domain. And the sequence is Fn. So, okay, so with sequence, you know, sequence is actually a map that takes integers into the space you want to look at. In this case, something like this, and you know that for sequences we don't write f of n but f down n, and you know all that. Okay, so take a sequence which is defined as the following set of functions. It's defined as the sine of 2 pi nx, and this for all n in n, and by n I think I mean n star here, so we don't take the 0. Is each of these guys once continuously differentiable on this interval? Well, of course it is. Okay, so you can look at this sequence. Now, what is of each single member of the sequence, what is the maximum norm? Well, the maximum norm, you need to look over this interval at the maximum absolute value of that the function takes. Well, it's of course 1, because the sign goes between +1 and -1 on there. So the maximum norm of each individual member of the sequence is 1. Okay, good. So, but then, if this is what you take, and you say, why would I look at the sequence? Well, let's look at it. Then you look at the image of this under the P. So what's Pf of an individual member of the sequence? I pick one member, I evaluate Pfn. Well, that's a function, so I best give it by telling you how it looks at a certain point. Well, the derivative of that is 2 pi n cosine 2 pi nx. It's all very, very innocent. Well, let's calculate and this is a sequence, so this is clearly, so these fn's are clearly all once continuously differentiable. I just write the C1, but it's really important on this compact interval. And here these guys, these Pfn's, they are clearly C0 because they're the derivative, and we are guaranteed this is once continuously differentiable, so the result is continuous. Everything is in perfect order. Now let's calculate the maximum norm of the results. So, well, I argued why you have the norm on both spaces. Now, you look again over the interval 0, 1, and you look at this. You know the n is actually positive. And then you see, this is 2 pi n absolute value, because the cosine, again, on this interval ranges between 0 and 1. But because n is non-negative, this is simply 2 pi n. There you go. Okay. So what do we therefore conclude? Thus. So now you wonder why we looked at the sequence. Didn't we just want to calculate the operator norm? There was no talk of sequences in the operator norm calculation, right? Keep this in mind. And now I show you where the idea comes up to use a sequence. Okay? So now assume we hadn't done this. So you dream about this later. Okay, so now let's start naively. P is not bounded. What do? Well, we try to calculate this guy. We try to calculate the operator norm of P, which by definition is given as the supremum. Let's take the definition where the f, where you take any f from C1, because it must be in the domain, any f of C1, of Pf with respect to the maximum norm by f with respect to the maximum norm, only applied to those in C1. Now, I want to show that it's unbounded. So it's enough to show that it's larger than infinity. Okay? I mean, if I can show it's larger than infinity, then it's infinity. So so here I don't have an idea what to do, because how on earth do I look at every possible C1 function? I don't have the space under control. It's a massive space, infinite dimensional space. I cannot check this for each element separately, right? I don't know how to even start. But it would be enough, and this is of course the analysis in functional analysis, it would be enough if I knew that this is greater or equal to, and at the end, infinity. And I know, okay, then it's not finite. So I make an estimate. Now the supremum is let's for simplicity say the largest value assumed here. You know, it's the lowest upper bound of the values, okay? But for thinking, let's say it's the largest value. Now what happens if I restrict this set, if I make the set smaller? Well, all that can happen if I restrict the set sup for f from a smaller set than this one, it can only be that the result becomes smaller. You agree? Because if I take another one on top of the one that's here, that's in here but not in here, that could make this one bigger. So this must hold. Is that clear? Now the question is, to what smaller set would I restrict? Well, of course, to a smaller set that yields infinity here. So a subset, a sequence, that's where the idea of a sequence comes in. If I say the f should be one f that's contained in this sequence, because the sequence is a subset of C1. In this step, I made the domain from which I take the f's smaller. Okay? So that means if I can find a sequence, and that's where the idea, where the cloud comes in, so slowly it dawns on you, if I could find a subset, for instance, the images of a sequence, such that I can conclude that this equals infinity, then I'm done and I showed it's unbounded. So you need a suspicion here. Okay, but this is clear now because this equals, this is the sup over all these guys. What is Pf? So if you do this, you can write this as sup n from n, and you use here immediately the Pfn by Fn. Agree? That's exactly that. But we calculated this. This thing here, Pfn, maximum norm is 2 pi n, and this guy down here is 1. So the result is 2 pi n. Well, it's 2 pi n, the supremum of n in n, 2 pi n. So if you go over all n in n, you know the supremum is infinity. Okay, so the actual idea strikes here. This is what you get from the definition. And then you're at a loss unless you get an idea. And that's one of the tools in your toolbox now. Try to construct such a sequence, and then you can show it's unbounded. Okay? Okay. So it's not bounded. So remark. Apart from the minor details, and of course that's meant ironically, apart from the minor details that in quantum mechanics we look at Hilbert spaces, and here we only looked at a Banach space, but you know every Hilbert space is a Banach space, okay? Look at Hilbert spaces and do not use the infinity norm. In quantum mechanics one uses other norms, okay? Do not use the infinity norm, and I could have, well, let's leave it like this. And that in quantum mechanics, the momentum operator which you have seen in experimental physics, right? The momentum operator is defined as, well, if I don't talk about domains because that comes later, is defined as it acts on a function or then on a on a Hilbert space element as minus I h bar. And if you're in one dimension, simply by the derivative. Well, so you've seen this, right? This is what, have you not? No, well, it doesn't matter. Anyway, so this is the momentum operator in quantum mechanics, one-dimensional quantum mechanics. Apart from these minor details, the previous counterexample is a harbinger of the fact that the momentum operator, because it's also a derivative operator, in quantum mechanics is not bounded. So it's just a remark. We'll see this much later. Neither is the position operator. Or neither will be. We will see that the position operator is also not bounded. This just as a warning. We look at bounded maps for a while, but finally we need to transcend bounded maps. So in order to follow the course over the entire semester, I think it's inevitable that after each lecture and before the next lecture, you really try to understand every equal sign in the entire lecture, because otherwise, with time, the material becomes unmanageable if you can't really follow with full command of what was done before. Okay, so now we have an important theorem. Now we look at the set of all such bounded maps. The set, we call it curly L, meaning linear maps, of all linear maps from a, well, I'll write it down. It's all the linear maps A from a normed space into a Banach space, as before, from a normed space into a Banach space. Which is, of course, linear. Okay, I mean, we'll not look at nonlinear maps ever. So, in doubt, it's linear. If you look at all such maps that are linear and now it comes bounded, that's important, and bounded, this set, so it's not all linear maps from here to there, it's only the bounded ones, is a Banach space. If equipped, well, if equipped with the pointwise addition again, so I'm not saying this again and again. You know, if you have a space of maps, you can always make a vector space out of it by adding them, defining pointwise, la, la, la. But, so this is now assumed, equipped with the operator norm. And that's the norm we constructed before. And you know that norm only exists for bounded operators. Hence, we restrict the set to these guys. And so sometimes, I said I will not write an index down there, but sometimes if I wish to emphasize, I might write something like this, because that's the space on which it acts. This is a Banach space. Now, let's provide the proof for that, which also contains a number of interesting insights. So we need a strategy to show this. And of course, minor steps, which I'm not going to spell out, is define the plus on the space, define the S multiplication on the space, show Kani and Adu, but this is almost immediate from the fact that W is a vector space. Show, we also haven't done that yet, show that the operator norm really is a norm. It's all very simple. You do this, and maybe it's a good exercise beyond the problem sheet. Yeah, do that. Just once for completeness. Most importantly, maybe this, because it's a little new. So those are the minor steps. So you get the whole setting. It's a normed space. Now, how does a normed space become a Banach space? Or when is it a Banach space? If it's complete. So, and complete means we need to show, now we need to show it that it's complete. Well, it's always a little bit unnerving. But once we have shown it, we can use it everywhere. Oh, I know it's a Cauchy series. Oh, I may already assume it converges. And that's fantastically convenient or even important to prove the various theorems. So the strategy, to show, what really remains to show at this point is that LVW with this norm is complete. And that means that we need to show that every Cauchy sequence already converges. And there is a strategy we're going to follow when doing that. The first thing is assume A sub n is a Cauchy sequence in the space we're looking at. So this is the starting point. I take one, any Cauchy sequence. And now the strategy is the following. First, construct a candidate for the limit of this sequence. We don't know yet there is a limit because we don't know yet it's complete. This is to be shown. But we take a Cauchy sequence and then we do something. You say, well, that could be, if there's a limit at all, this could be the limit. Okay, so construct a candidate for the limit. So what would that candidate be? Well, the candidate would be an element in here, because we need to show that the limit of the Cauchy sequence lies in here. So we need to construct a candidate map from V to W that's bounded. So we need to, once we constructed a candidate map, we need to show that it really lies in here, show that A really is linear, because you can construct a candidate map from a sequence of maps, but it could be it fails to be linear. Okay? Show that it's linear. Also show that A is bounded. Well, of course, if you want to show it's in LVW, that doesn't only need to be linear, the candidate, it needs also be bounded. And once you've done all of this and using all of this, and that's why the order is this way around, then you show that this Cauchy sequence really converges against the candidate. If you take any Cauchy sequence and you can construct a map A such that the map A, that the sequence converges to A and A lies in the space and not outside the space, in the space, then this is completeness. Okay? So this is the strategy we're going to follow. Okay, so the first step, we observe that if AN is a Cauchy sequence, I only write Cauchy in L, I only write L, not LVW for brevity. If AN is Cauchy in L, then it follows that for any F you take in the domain, the sequence constructed by applying the nth element of the sequence of operators to the F, this of course again yields a sequence. This time I write it like this for no good reason, is a sequence, but this is now of course a secret in the target space, right? Is a sequence, and it's not only any sequence, it's again a Cauchy sequence. So that's the point. If a sequence of maps is Cauchy, then the sequence of its images of any element is again a Cauchy sequence. If I say we observe, we should answer the question why. Okay, so you can keep this in mind as a general thing. Well, what you need to do, you need to check whether this is Cauchy, if this is Cauchy. Okay, let me spell it out once in detail, but in the future okay, this is going to be anyway. So let's assume this is Cauchy. What does it mean this is Cauchy? That means for every epsilon greater than 0, there exists an n in n such that for any pair nm greater or equal to n, it's true that an minus am, well, in the operator norm, what other norm, is less than epsilon. This is the assumption. This is an is Cauchy. So now we observe in here, in thinking about it, we look at ANF minus AMF, where we're talking about any F in V. We know, so let me write it down. So for any F in V, it is true that this thing is, of course, AN minus AMF, using the pointwise addition on the operator space. And now this operator norm, no, it's not the operator norm, nonsense. This is the operator norm, but this must be the norm on W, right? Because we applied it to an F, then we get an element in W, an element in W. Now I claim this is less or equal than the operator norm of an minus am times the norm of f on v. Well, how do I know this? Well, this is the definition. This comes from the definition of the operator norm. Remember, the operator norm is the supremum of these guys divided by these guys. So if I no longer take the supremum over all f, but I just pick blindly an f, this will always be larger or equal than this one, right? For any fixed f, this is true. But now, since this is a Cauchy sequence, this is less than, from here, this is less than epsilon times the norm of this f. But I started with an f. So with these quanters, you start with for all f, this is true. But for any specific f, this is a finite value. So you could have made this into a very nice proof of this being Cauchy, what I claimed here, if you had chosen here epsilon divided by the norm of this. Well, okay, but that's just mathematical aesthetics. This already shows that this is also Cauchy. You can conclude this. Okay, so the y bracket closes. And it's only because this is bounded. No? It's only because this is bounded. So bounded operator, sequence of bounded operators takes an element of the target into a Cauchy sequence of bounded operators takes an element of the domain into a Cauchy sequence on the target. Okay. So later on, this will barely be worth mentioning. So why is this interesting? Well, it allows us to construct the candidate map already. But since we know that the target space W here is a Banach space, that W with its norm is Banach, we know that the sequence ANF has a limit because it's a Cauchy sequence in W. It's a Cauchy sequence in W. Because W is Banach, we can conclude this exists in W. This number, this limit exists. So we define our candidate map we call it A, so not to be confused with any member of the sequence. Well, there are A1, A2, A3, but there's only one map A. The candidate map A is supposed to be in here. So it certainly needs to be a map from V to W. And we define as an F is taken to. So candidate map, I should say, candidate map for the limit of ANs. Now you see, this is a limit in W. Now it's a candidate map to be a limit in LVW. So you need to keep track on which space we are. We have a Cauchy sequence here. No, sorry, we don't. This is the domain. We have a Cauchy sequence on this LVW. From that, we constructed a Cauchy sequence on the W. And what we want to show, finally, is that we can construct a map A, which is the limit of the Cauchy sequence on LVW. Okay? Yeah, that is that. And that we need to define. So we need to keep track of what we're doing. So the candidate map to be the limit of the ANs in LVW is that I take here the limit. I define this as the limit of the ANs as it acts on the F. And I know I can do this because I just ascertained that this limit exists in W. So all I know so far, this is a map. This is a map. I don't know it's linear, and I don't know it's bounded. And I don't know that it's the limit of the ANs. I don't know yet. These three things I need to show. Once I showed them, I'm done. Okay, so let's show that our candidate map is linear. So what do we need to do? Well, we apply it, we take it, and we apply it to a sum of two elements in V. What is it? Well, our candidate map A is defined as this limit. So it's clearly the limit n equals infinity over the individual ANs applied to this. Okay? Very simple. Now, we need to be very careful with calculating with limits here. We have all these rules. The limit, the sum of the limit is the limit of the sums and so on. Let's be very careful. We can argue with continuity. So, first of all, again, later we will not do it this explicitly. This is ANF plus ANG. This plus was in the space V. This plus is now in the space W. Why is this allowed? Why may I write this plus sign, this equal sign? Yeah, that's it. It's the linearity of the ANs. Each AN is linear, so I can do this. Very simple. Now, what I would love to do is the following. I would love to write lim n to infinity ANF plus limit n to infinity ANG. Because, well, I need to justify this, okay, in a second, because if I do that, I of course get by definition AF plus AG, and I'm done with the additivity. Then I do a lambda f for a complex lambda, right, in a similar fashion. Similarly. And then I'm done with linearity. The only question is, why may I do this? Why may I pull this apart in two pieces? And, well, if you think topologically, what we have here, the plus is just a type of map, right? I mean, that's what we have in the vector space case. The plus that is written here is the plus W. What does it do? The plus W takes two elements from W and sends them to a W. Is that right? Now, under what circumstances, if you take the abstraction from this having two entries, so in a sense you have F and G are being sent to the map plus W eating F and G. Okay? Now, this is just one element in a Cartesian product, and the question is, may I, if I consider it as such a map, I could write this map by a capital M, M-like map, right? The question is, may I do the following, L n to infinity M of a sequence. Well, in this case, it's something that depends on n, Fn. May I pull the map out equals of the Fn's? May I pull the lim into the map, or may I pull the map out, however you want to look at it? And you know when this is possible. When is this possible? When can you do that? Well, you can certainly do it when the map is continuous. So we need to decide whether this map with this domain and this target is continuous. What do you need to know? You need to know a topology on here, and you need to know a topology on here. Then if the pre-images of the open sets are all open, then it's continuous. Do we have a topology on W? Yes, we do. W is a Banach space. We have the softball topology, like the standard topology, if you wish. What do we do on a Cartesian product? Well, you can establish the so-called product topology. If you don't know that, look it up what it is. Certainly you can do it. And then this thing can then be shown. It can be shown that the addition on a Banach space is continuous. So what we argue here is, indeed, plus on W is continuous. It sounds at first sight a little funny because what do you mean addition is? I mean, I know what a map being continuous means. Well, addition is a map. Okay, if this is continuous, you may do this, and in fact, it always is. So from now on, you can remember, okay, you have a plus on a Banach space, you can pull it out. This rule applies. But if you want to go back and show this, you go to this thinking. Okay? Right, so fine, we have shown that A is linear. If you also execute this, this works exactly the same with the S multiplication being continuous. Okay? So if so what's your feeling? Are you shocked by all the indices and all this stuff, or is it okay, or is my speed okay? Okay, you stop me, please. Okay, you stop me. You ask questions anytime, and I assure you, if because we do all the proofs and all the details, if you review the lecture this afternoon at home, you should be able to make sense out of every single line I write down. So we showed our candidate map is a linear map, but what we now need to show, it's actually an LVW. It's a bounded linear map. A is bounded, because otherwise, even if we later on show it converges somehow, it needs to converge in this space. A is bounded. How do we show that? Well, we want to calculate the operator norm. Okay? And we do this by calculating the numerator of the definition in this sub, because that's an important piece. So we calculate ANF. No, do we do this? No, we don't do this. Hang on, I want to do something different. No, I want to calculate this. I want to calculate AF, not the operator norm, on W. So I take our candidate map, I apply it to any F, right? So for all F in the domain, I look at this guy, which appears in the definition of the operator norm. Well, first of all, I write what it is. It's the limit n to infinity ANF, because that's our definition of the candidate map. It arises in this fashion from the Cauchy sequence AN acting on F. Now, I would love to pull the limit out. What would I need in order to justify such a step? What would I need to know? It's the argument we just had. What do I need to know? Continuity of the norm. Continuity of the norm. I need to know that the norm on a Banach space is continuous with respect to the topology it induces and the topology that is induced by that topology on the Cartesian product of the W's. Okay, so do that at home. Okay? Show this. It's a good exercise in topology. It's a good exercise and a good reason to look up the product topology. So you see, we want to calculate something. You get ideas of what you need. Well, then go and try to prove it. Okay? So we want this guy. Now, looking at this guy, this is this limit. Coming?
At what point do we need the product topology in this case?
Nowhere. Thank you very much. Yeah, that's of course nonsense, because this guy, of course, goes for. So what you need is the standard topology on here. You need the standard topology on here, and the topology. Yeah, that's easier than the addition example. I'm sorry. Thank you very much for the remark. Excellent. Yeah. Okay. We have this. Now I think we need to go to the operator norm. Yes, of course. Now this thing here, I now claim, is less or equal than, I keep the limit, less or equal than A. Oh, hang on, what do I want? I'm sorry. Hang on a second. Yeah, of course, yeah. is less or equal than the limit of the operator norm of the ANs times the F on the W. So that's the operator norm, that's the F. Why is this true again? Well, I picked a specific F. The operator norm is the largest result you could get for this divided by this. Well, if I pick a particular F, that could have only been less than if I use the operator norm. Now, the point is, for any specific F, this is of course finite. And so what I want to look at is whether this actually is also finite, whether this is finite. Is this finite? Yes? Y. V. V. Yes, you're right, of course. So here it's W because that's the result and that's the norm on V. That's right. Any F on V, it's the norm on V. That's right. Thank you. So this is finite, we know. Now the question is, we know that for each individual AN, the operator norm is finite because the ANs are bounded, because there's a sequence in this L space. But can I already conclude that the limit over all of these is finite? Well, yes, I can. Indeed, it is. Since AN is Cauchy. Why is that? So what we need to show is that if AN is a Cauchy sequence, that then this limit is bounded. And so what does it mean if AN is Cauchy? I write it down once more. Epsilon greater than 0, for all epsilon greater than 0, there exists an n in n, such that for all nm greater or equal than n, it's true that the pair an minus am, that this is less than epsilon. That we know. Okay, it is Cauchy. Well, from this it follows in particular that if it's true for all nm greater or equal to n, I can replace this part here. I can replace it by for all n greater than n, it's true that an minus a capital N, whose existence is guaranteed, so this remains, is less than epsilon. That's right. So now I want to write this using the triangular inequality as an minus an. Now this cannot be right. This must be less or equal than this. I claim this follows from the triangular inequality. You think you can or you cannot?
I'm thinking.
I think you can. Okay, so let's see. So you have a plus b is less or equal than a plus b norm. Okay? And so I need to let b equal to c minus a. Then this turns into a plus c minus a is c is less or equal than a plus c minus a. So I get c minus a is less or equal than c minus a. Everybody happy? Okay, it's just a simple thing. Okay, so I have this. So I know for every epsilon greater than 0, there is an n such that difference is less than epsilon. So that means for every epsilon greater than 0, there exists an n in n, such that for all n greater or equal to n, it's true that an is less than epsilon plus absolute value, operator norm a n here. This settles it, because I know that whatever the epsilon is, I can always make this smaller than that. Okay? And hence the limit is bounded. Hence the limit of the an absolute value is finite. This is finite. Okay, so it is. Why? Since this is true. But then we go up to here, so what do we see? We see that this norm here is less than finite times finite. This is less than infinity. Okay? Okay, it's true, but it's not the point. In order to make sense out of this, I first need to divide by this. Therefore, AF on W divided by F on V is less or equal than the limit n to infinity of the ANs. We just showed that this is less than infinity, that this is bounded. But if for any f it's less than infinity, no, that's not good enough. What am I doing here? No, yes, for any f there's no limit anymore. Yeah, if for any s, no, that's not true. Confused. I'm sorry. And for any individual f, it would be less than infinity. Yeah, but it could, for each f, it could get bigger and bigger and bigger. It could be that for a particular f, this expression is 20, that's less than infinity. For the next f, it's 30, it's less than infinity. For the next f, it's 40, it's less than infinity. It could go up, couldn't it? Confused. Hang on a second. No, it's not true. You know why? Because everything that's said there is for any f already. Yeah. No, okay. Good. Yeah. Perfect. So what is to be concluded is that our candidate map A is bounded. So what have we achieved? We have constructed from our Cauchy sequence of the ANs, we have constructed a linear bounded map. That we have done. Now, this could be a very useless linear bounded map for our purposes, but what we finally need to show is, well, this Cauchy sequence really converges exactly against this map. So, fourth step, finally, show that Cauchy sequence AN converges against A. So what do we need to show to look at that? Well, let's start. Since AN Cauchy for all epsilon greater than 0, there exists an n in n, such that for all nm greater or equal to n, it is true that an minus am is less than epsilon. That's again the Cauchy assumption from the very beginning. And so this is the operator norm, right? If we talk about convergence of bounded operators, we use the converges in that space. The space carries the operator norm, so it's convergence with respect to the operator norm. Okay? Question. Later on, when we look at not necessarily bounded operators, at unbounded operators, can we still define convergence with respect to the operator norm? Well, of course not, because the space of unbounded operators doesn't carry the operator norm because it diverges. So then we will talk about strong and weak convergence in a way that will be a slightly generalized notion of convergence. Okay? So always think, oh, this converges against it. This, always think on which space with respect to which norm. Does the norm even exist on that space? Okay, so and there are a few subtleties, and at first it seems a little fuzzy, but really there are only very few elements you have to look at. If we don't look at them in detail, you're totally lost, right? Then no argument works. Okay, so you have this here. So now this is the operator norm, and hence we can already conclude again that this is larger or equal than, because it's the supremum, it's larger or equal than an minus am acting on f divided on the W space divided by f on V for just any f that you can find, and in the order of quantors for all there exists, such that for all there must be okay. It must go here. So this is equal to this, and this is for all f in V. Right? Why? Well, if you don't look at all of this, this is the definition of the operator norm. The operator norm is the supremum of all these over all f's. But if you take a specific f, so this is the conclusion, if you take a specific f, then the result will be smaller or equal to the operator norm. Okay? So this is what you have here. Right. So now what we can do, so that means, so I write again the whole line, epsilon greater than 0, there exists an n in n, such that for all nm equal to n, it is true that for all f in V, we have an minus am now applied to this picked f is less than, because we have a sequence of less than signs, is less than epsilon times f norm V. So I multiplied this over there. So this is really weaker, right? Because I didn't use that this is exactly equal to supremum. I made an estimate here. This follows here. Okay, sorry, and this is this guy here, and this is the result on W. Aha. Now, you will see that what is remarkable here, the left-hand side depends on n and m's, and the right-hand side does not at all. So we can therefore conclude that if we take the limit m to infinity, so therefore the limit of taken m to infinity of an f minus am f w will not have the slightest effect on our estimate, because the right-hand side simply does not depend on this m. Moreover, now the W norm is continuous. Hence, we may have the limit jump in. So therefore it follows that an f minus the limit m to infinity well, here it has no effect, of AMF, is less than epsilon times absolute value of V. Aha! But this gentleman here is AF, you remember? It's our candidate map AF. Now, we took the limit here, so I know it's true for any m greater than equal to n, therefore I can conclude this. But what I should still keep here in front is that for all epsilon greater than 0, there exists an n in n, such that for all n greater or equal to n, we have this. So kind of this Quantor sequence is still in front of here, if you come from here. You know that it's very important that you keep the sequence, right? For all there exists is very different from there exists one for all, right? So you cannot swap the order of the Quantors, and therefore I was so picky to write the for all f here. You couldn't write it here, you get a totally different statement. Okay, so therefore you really need to separate off where you use it. It's like local variables in programming or something, okay? Be very careful, otherwise your conclusions are wrong. Okay, fine. But now we have this, and that means there exists. That means there exists an n in n such that, so for all, well, it means for all epsilon greater 0, there exists an n in n such that ANF minus, such that for all f in V, ANF minus AF divided by, now I take this from the other side to here, f in V, this is in W, is less than epsilon.
The index of the first AN should not be either the capital N, or you should introduce the other quantum for all.
So I started from here. Let's see whether I see what you mean. We know it's again a new argument, so this one was finished. Now we have for all nm greater equals n, this is true for all f. And now what I did is I said, well, if it's true for all m, then I can take the limit of that. So I have an, am, I take the limit. I go down here, I took the limit, I pulled it in. So I don't see why this should be the, so there's still this quantifier over the little n.
Yeah, but then you have to somehow denote that it exists, or you have to
Okay. I'm sorry. You mean here?
Yeah, exactly.
Oh, I'm sorry. Thank you very much. And then for all f in V, you have this. That's right. Aha. So now we need to make yet another estimate, and the estimate we need, and then we think about whether it's right. The estimate we need is this is less or equal than, well, let me write it here. This is less or equal than the operator norm an minus a. Now, why is the operator norm less or equal than this? Well, the operator norm...
But it's for all f, so the operator norm is included.
Yeah, very good. Yeah, very good. Okay, so it says for all f, this is true, hence it's true for the supremum. Yeah, okay, thank you very much. That's excellent. Epsilon greater than 0, there exists an n in n such that for all n greater or equal to n, the operator norm an minus a is less than epsilon, which is now stronger than Cauchy. It is convergence. So indeed, we're finished. We proved that the space of all bounded linear maps equipped with the norm, with the operator norm, is a Banach space. So let's have 5 minutes break till past, and then we continue. Or any more questions at this point? Okay. So shall we continue? So there was the wish to move the Monday lecture to 1 p.m. rather than 1:30. So move it to the past. Is that fine for everyone? No. Okay, done. So,
Just integrating Regensburg students.
oh, okay, I see. Good. Well done. Okay, so an important insight is the following. It's about the domain of a linear map, and it's called the BLT theorem. So an important insight about the domain of a bounded linear map is the so-called BLT theorem. And for once, these are not people, the BLT. It's called the bounded linear transformation theorem. Bounded linear transformation theorem. And I'm not entirely sure. Of course, a linear map, you could call it a linear transformation on the vector space. So actually, in our terminology, it should probably be called the bounded linear map theorem, because that's what we said. So transformation is nothing new. And my suspicion is that people stick with BLT because BLT is a very well-known acronym for bacon, lettuce, and tomato sandwich. So, so that's my suspicion why this keeps surviving instead of becoming the BLM theorem. Now, the thing is this. Consider a bounded, that's important, a bounded linear map which is densely defined on a domain. So let's say the map is called A. The map is called A, and it has a domain A. So far we called the domain V. Okay? But now assume this domain that so far was called V. Maybe I should have written everywhere DA. Okay? But it could be that this is only the subset of some V. Okay? Maybe I write it like this. Look at a bounded linear map that's densely defined so that the closure of the domain coincides with the normed space. Okay? And yet again here, Banach space. Then it's a natural question, well, you define it only on a subset of the normed space. It better be a linearly closed subset, so not only a subset, a vector subspace. But the question is, could you extend the map? Could you fill in the points that don't belong to the domain, but that belong to the V, such that you have an extension of this map to the larger domain? That's the question. So consider such a map. Question: does there exist, or is there, does there exist a so-called extension? That's a technical term, an extension of the map A, dAW. What is that? So it's a question/definition, namely definition of extension. Does there exist an extension of A, dA to W that is a map, well, a linear map, that is a linear map, let's call it A hat, that goes from the entire V, and not only from this dense subvector space, into W, such that A hat, if it acts only on an alpha that comes from the original domain, so if on the original domain the extension agrees with the original map, Well, that's an extension. You make a map, you add additional points to the domain, but you don't change its values on the domain you had before. Does there exist an extension of A? Can you extend this here? And the theorem, the BLT theorem, says there is a unique such extension to a bounded map A hat. Extension of such an A to a bounded map hat A. Or in other words, before we do the proof, in other words, because this is a unique extension, we may and always will extend any bounded, and again, bounded is the key word, any bounded linear map to the entire normed space at hand. So we will not bother about thinking about bounded maps that are only defined on a subspace of a normed space. We'll always extend it to the full normed space. We can always extend it. In quantum mechanics, that will say operators whose measurement values have a bounded spectrum, I translate this for you, they can later on be defined on the entire Hilbert space. But unbounded operators cannot be defined on the entire Hilbert space. Okay? So we'll come to that. An aside, so you say you haven't seen the momentum operator. Have you seen something like the position operator that acts by multiplication on a wave function? Not. Who has not? Okay, so no aside. Okay, no aside. Okay, proof. So how do we do this? Well, we start with such a map. Let's take A, dA to W with the usual, so also write A is in L, dA, W. It's a bounded linear map. Now I want to construct its extension. So the first step is take an F that lies in V. So you see the domain of A is only a subspace of V. And now, however, I take an arbitrary element in V. Well, if it already lies in dA, it lies in dA. But if it doesn't lie in dA, then consider a sequence Fn of Fn's that all lie, the entire sequence lies in dA, but such that the limit of those guys is this element outside, possibly outside dA, is this F. Why can I do this? Well, I can do this because dA lies dense in V. Because if you're dense in it, you can actually make a sequence that converges there. Like you can find a sequence in the rational numbers Q that converges to square root of 2. Right? It's the completion of that space. So that you can always look at. Now, and this F and the extension, so the A is only defined on each Fn, and only the extension A hat should also be defined for the limit, which might not lie in the dense subset. That's the idea. So let's look at this. Then this Fn sequence is certainly a Cauchy sequence. Why is that? Why is Fn certainly Cauchy? Yeah, it even converges. Every convergent series is Cauchy for Cauchy is convergent, you need completeness, but every convergent one is Cauchy. But then we had this argument before. You take a bounded linear operator and you apply it to it, this, because the A is bounded. The image of this is again a Cauchy sequence, since the A is bounded. Very important. So Fn is Cauchy on dA, and AFN is Cauchy on W. Aha, we have a Cauchy sequence on W constructed. What do we know? Since W is Banach, what do we know about the Cauchy sequence A and F? It converges. We know there exists, well, we know that the limit n to infinity of A and F exists in W, because W is Banach. Every Cauchy sequence converges. Define the extension A hat as the map A hat prepared to eat just anything in V and giving a W. And if you take an F in V, you can always find a sequence Fn that goes to F, right? Because the F and the sequence Fn, each element lies in dA. Why can you always find that? Because dA is dense in V. And you find one such sequence, and we then have to show well definition, and you define the A hat of F to be the limit of the AN, of the A acting on the Fn. The A can only act on elements in dA, but the Fn are in dA. You take this limit. That's your definition of the extension. Now we have to show that what we defined here is what we actually want. So this can be defined like this. The question is it an extension? Okay, but is this an extension in the sense defined just before? Well, let the F be in the original domain. Then the constant sequence Fn, defined as F, is a sequence in dA that converges against F, very trivially. And then clearly A hat acting on such an F, maybe I should have called it alpha, because before I called it alpha. Right? And then A hat of alpha being defined by here as the limit of the ANs acting on the of the A acting on the Fn's is the limit of n to infinity of the A acting on the alpha, but the n no longer plays a role. This is A alpha. So it is an extension. Okay, it is. But is it linear? Well, look at it. We start the other way around. We take A hat of some F plus the A hat of some G. Do you want to go this way around? Well, let's try it. This is lim n to infinity A on the Fn plus lim n to infinity a on the Gn, because for the Fn and the Gn, you can find sequences converging to it. And if you have the feeling, well, that might not be unique what sequence you choose, you're absolutely right. We will still have to show well definition. But we do this here. And now you have a plus on W in between here. But the plus on W is continuous as before. Hence, again, we can write one limit of a Fn plus a Gn. And then again, because of the pointwise definition, we can actually write this here. But then we actually know that the A is continuous. So I can now jump the limit into here. No, I shouldn't. Hang on a second. Aha, I define now a sequence that I call capital Fn, that is the sum of these two guys, and I know that capital Fn converges against f plus g. Because Fn converges against f, Gn converges against g, so these two converge against this guy. So this thing is, by the definition of the extension we gave, is a hat f plus g. Okay, and similarly, for lambda, a hat of some f in V equals a hat of lambda f for all f in V. So we have this bit. Yes. So we still have to show, but I leave you that as a homework. It's very simple. Still have to show that the extension is bounded, and in fact that it's well defined. Remains to show, check, that first of all, this extension a hat f that is defined as lim n to infinity a fn for some fn sequence in where each element lies in the dA and this lies in V, for some that this is well defined. That means you need to choose another series, choose another, not series, sequence. Choose another sequence, Gn, that goes, however, to the same f, of course, okay, and show that that the limit n to infinity a fn is the same as if you took the other sequence. This still needs to be shown. Of course, you again use that the original A you have there is bounded. And it also remains to be shown, second, that the A hat itself is bounded. That's not difficult. And that, indeed, the operator norm of A hat exactly coincides with the operator norm of the A. That means extending a bounded linear map that's defined on a dense subset to the completion of that subset, V in that case. That means taking on additional points in the domain and putting the values of the map such that the whole thing is then still bounded and hence continuous. Well, I put it on the problem sheet. Any bounded map is necessarily continuous. That doesn't change the norm. It doesn't change the norm. So really, nothing happens if you have a bounded operator defined on a dense domain. Nothing happens if you complete the domain. You take all the limits you can have to it, okay? And you'll get an extension of the bounded operator to a bounded operator on the full space, okay? And this is why we usually don't bother to say, oh, a bound operator on some domain where we write the whole space, okay? And this is the BLT theorem. Right. Okay, two more important definitions. Then we're done for today. Could you pass around a piece of paper, write your name and your email address, and then you pass it around. Everybody writes his or her name and email address, please, so I can send you information concerning the course. Yeah, but that was a different group. You're only a subset. Okay. So the BLT theorem is very important. So recall, LVW is Banach already, even if V is only normed. So, well, this W needs to be Banach. But then all maps from a normed space into a Banach space, that set equipped with the operator norm, is a Banach space, even if the space you start from is not. Okay? That's just a fact. Definition. Let V, comma, norm on V be a normed space. Of course, nobody prevents you from taking it to be a Banach space, but maybe it isn't. Let V be a normed space. The dual space with respect to V and its norm is V star equipped with the operator norm. You say, what operator norm? Well, with the operator norm on L, V, comma, complex numbers. So it means this is the same as L of the normed space and the complex numbers, which then carries a natural operator norm. And not only that, so it's this norm on there, and this is a Banach space. So the dual space of a normed space is a Banach space. We already know this because we had proven that any set of bounded linear operators is that. And the dual space, you see, the dual space consists not of all maps from V to C. The dual space of a normed space consists only, according to this definition, of the bounded maps from V to C. Remember from linear algebra, the dual space of a vector space is the space of all linear maps from the vector space into, say, the complex numbers. But now we have more. We have infinite dimensional vector spaces. We have norms on them, which we want to have. And we define the dual space to be only the bounded linear functionals. So if you want to say dual vectors or covectors, right? Covectors are bounded linear functionals. By functional, we mean something that lands in C, V2C, okay? Linear functionals. And homework, but I think I'll put this on the problem sheet. Homework is bounded implies continuous. Okay? So if you know it's bounded, it's necessarily continuous. That can be shown rather easily. This goes via Lipschitz continuity, and that implies continuity. Okay? And again, you have more structure than in an arbitrary vector space, and you only want the bounded functionals to be in the V star. Otherwise, you run into trouble. So one more definition. A sequence Fn in some normed space V is said to A, converge strongly if for every epsilon greater than 0 there exists an n in n such that for all n greater than or equal to n, Fn, well, if there exists an f in V such that the difference to this f as measured with the norm on the space is less than epsilon. So you say, oh, this is nothing new. This is only the old definition of convergence. Okay. So what so far we called converge, we now called convergence, we now call strong convergence. Not always, only if we want to distinguish it from the notion I define now. So this is the same old thing. As convergence is just a change of terminology, and B, a sequence converges, you guessed it, weakly. It's not only once a week, but here A, converges weakly if for all L in the dual space of V, how was it? L of Nn converges to, weakly, strongly to F in V. Let's write it like this, to a specific F. Converge to F in V. If for every L in V star, LFN converges, well, strongly, but this is on the complex numbers, right, to L of F. And on the problem sheet, that you're only going to hand in middle of next week or something, on the problem sheet you're asked to show that a strong convergence implies weak convergence. And in the first case, we also write S-lim Fn equals F. In the second case, we write W-lim n to infinity Fn equals F. These are two different notions of convergence which we're going to make use of. Any questions? Okay. Did Stefan Götzinger talk about problem class tomorrow?
No, it will be on the 30th of April.
So next week?
No. Week after.
The week after. So then mine is next week or something, probably. I guess, yes.
6 weeks. No.
Yes. If you wish, we could meet on Thursday afternoon to discuss if you have questions. It's on Thursday afternoon, right? The problem class. So tell me tomorrow whether there's interest. If there's not, I don't need to come. But if you want to, certainly. Yes. Yes.
Practice in class. Would you maybe be okay, or if you could shift it by 1 hour? Also found a room where we could do it.
2.
No, it's not
Impossible. Okay. Good. Okay, thank you.